everyone, welcome back to the channel. In today's video we're going to be discussing the Dirac delta, and we're going to look at how to find the Laplace transform of this discontinuous function. So let's get to it. So the Dirac delta is the mathematical representation of an impulse. So an impulse is something that happens at an instant in time. So for example, a surge in voltage would happen at a particular instant. The Dirac delta is also used to represent point loads on beams because you have a load at a singular point. So the way we represent that is P minus A. And this over here, that represents the Dirac delta, right? So it means that if you have an interval and say at time with times A, you're going to have something happening at that particular instant. So it's not like the Heaviside step function that happens over an interval. It's at one particular instant. We say that the Laplace transform of a Dirac delta is going to be e to the power minus as. So let's look at an example. So here we've got a function which is a discontinuous function. We know that because you see we have the Dirac delta in each of these terms. Inside of that Dirac delta, you'll see the first one is t minus 1, the second t minus 3, and the third t minus 4. And what this means is that something is happening where t is equal to 1, 3, and 4. So if we were to write this, draw this on a sketch, we would have an interval like this, and that is f of t. So that's 1, 2, 3, and 4. The first one is happening where t is 1, so there. So let's just write this one. That is 1, so this one is 1. The second one is happening where t is 3, and because you have a minus, it is going in the opposite direction. And you can choose which way is positive and which way is negative, especially when you're working with point loads in the context of strength of materials. So that would be number 2. And the last one happens where you have t equals to 4. And that is positive, so it is going up. Well, for this example, because I choose positive to be in the upward direction. There we go. So now, if I was to take the Laplace transform of f of t, and we remember that the transform of your Dirac delta is going to be e to the power minus as. So then, if I take the transform of f of t, I'm going to get 2 times e to the power minus s minus 4 e to the power minus 3s plus 5 e to the power minus 4s. And that's it. The Dirac delta is a bit more straightforward than the Heaviside step function. In the next video we're going to look at how to solve a differential equation with the Dirac delta in it. I'll see you next time. Bye.